Diagenesis and discovery. After burial, a variety of diagenetic changes in the rock, especially metamorphism, can easily destroy the shells and prevent their preservation. As discussed earlier, aragonitic fossils are much more prone to dissolution than calcitic fossils. So fossils that are made primarily of aragonite are discriminated against in the fossil record. For example, there are a number of calcareous plankton in the fossil record, including the foraminifera, the osteopods, and a group of tiny aragonitic planktonic snails known as pteropods. All three groups can be very abundant and in tropical surface waters, but as they die and sink to the bottom, the pteropods dissolve first because they are made up of aragonite, not calcite. Many calcareous oozes on the seafloor are not good reflection of the original plankton in the surface waters because the pteropods have been selectively dissolved away. In another study, Voigt 1979 censured used a living oyster bank and found over 300 species, mostly soft-bodied worms, of the shelly invertebrates. 16% nearly all the snails and many of the bivalves besides oysters had aragontic shells. Once these had dissolved, the remaining oyster community appears to be of low diversity, but this is a false conclusion. The only species fossilized are those with calcitic shells. The only species fossilized are with calcitic shells. Many apparently unfossiliferous rocks probably had fossils at one time, but diagenesis has removed them. This is usually hard to document, but McCarthy, 1977, described a Permian beach sand that had no apparent fossil until he examined scattered concretions. Inside the concretions, there were abundant fossils showing the original texture of the rock before groundwater flushed through to dissolve everything not protected by a concretion. The diagenetic history of a fossiliferous deposit can be very complex. The Miocene Lethal limestone of southern Austria, Dulon 1983, can be subdivided into several biophyses based on relative abundances of mollusks, corals, red algae, bryozoans, and foraminifera. However, a closer examination shows that these relative abundances are largely a diagenetic artifact rather than original ecological abundances. Calcitic mollusks such as oysters and scallops are well preserved in all fishes, so they dominate the heavily dissolved fishes. Aragonitic mollusks are preserved only in basinal muddy fishes. Aragonitic fossils represented by molds or replaced by calcite are found in the chalk and well-cemented limestone fishes. Aragonitic fossils are completely absent from the carbonate sand fishes. In this case, the degree of exposure to groundwaters and marine waters is more important than the original community composition. In summary, the original composition and groundwater chemistry are the most important factors in determining whether diagenetic changes are likely to alter or dissolve a fossil. Finally, only a small portion of all the fossiliferous rocks in the world happen to be exposed during just the few centuries when people began to collect them. Even a smaller proportion of those outcrops are ever seen by a qualified collected before the fossil erodes out and is destroyed. Thus, the chances of a given animal having the extraordinary luck of being preserved and collected by a paleontologist are extraordinarily small. Taphonomic research has come a long way since the pioneering studies of the 1960s and 1970s. Paleontologists can no longer afford the naively take the fossil record at face value, but must always keep in mind the taphonomic noise that may obscure the original biological signal. However, not all taphonomic processes are negative. Applied properly, taphonomic information can add to our understanding of the fossil record. And in many cases, we can appreciate dimensions of the past that would otherwise have escaped our notice. In that they form and honor roll that most paleontologists know by heart. These are discussed next. The Middle Cambrian Burgess Shale, British Columbia. In recent years, the most celebrated of all the Lagerstätten and the Middle Cambrian Burgess Shale from the Canadian Rockies in Yoho National Park, British Columbia. A few quarries high on the slopes of Mount Reed have produced over 65,000 specimens of mostly soft-bodied animals, representing at least 93 species. Most are preserved as flat impressions on the shells, although the trilobites are preserved with their calcified skeletons as well. These organisms were apparently transported from a nearby shallow carbonate bank into these anoxic deep water shells by submarine landslides where they were abruptly buried in fine mud and not allowed to decay. What is extraordinary about the Burgess shale is not just the preservation of typical Cambrian animals such as trilobites, but the great number of unique and bizarre soft-bodied animals that we would otherwise never know about. Although the majority can be assigned to existing phyla, many are clearly unique evolutionary experiments that belong to no living phylum. In his book Wonderful Life, Gold, 1989 argues that this window in time of the Burgess shale allows that there were many experimental phyla during the early Cambrian radiation that did not survive even to the later Paleozoic. Contrary to the long held expectation that everything in the Cambrian is simple, primitive, and ancestral to living groups, the Burgess shale shows that there was a great deal of experimentation in unusual body plans during the Cambrian, most of which did not survive. The Burgess shale is not unique in this regard. Lagerstätten from Xinjiang, Yunnan province, China, and Sirius Pacific Greenland have produced similar forms, showing that the explosion of experimental forms took place around the world in the Cambrian. The Upper Jurassic Solnhofen limestone, southern Germany. This deposit was first quarried because it yields extremely fine-grained slabs of limestone that were perfect for the acid etching process to produce lithographic printing plates. Apparently, these limestones were produced when fine lime mud washed away from the ocean into shallow, stagnant lagoon, which was low in organic productivity. So the rocks are not black with organic matter but white and completely hostile to all forms of life on the bottom. As animals died and sank to the bottom, there were no scavengers or decomposers to decay them, no current to break them up, and apparently they were rapidly buried as storms brought in new layers of brine mud. There are more than 600 fossil species preserved in the Sorenhofen limestone, including over 180 species of insects and many marine arthropods, especially crustaceans, such as a well-known specimen of the horseshoe crab Mesolimulus preserved at the end of its final trail. The most striking specimens are the terrestrial vertebrates, including numerous pterodactyls, which sometimes preserve their body outline and wing membrane, and all seven known specimens of the bird Archaeopteryx, complete with feather impressions. These specimens are important as the missing link between birds and dinosaurs, especially because the first specimen was found just 2 years after Darwin's On the Origin of Species was published, providing dramatic evidence for his theory. The Pennsylvanian Mason Creek beds, northeastern Illinois, exposures of the Middle Pennsylvanian Francis Creek Shale of the Carbondale Formation in the Mason Creek area of the northeastern Illinois yields nodules of siderite, iron carbonate that, when split open, preserve soft-bodied organisms in exquisite detail. Over 350 species of plants, the most diverse flora known in North America. 140 species of insects and over 100 additional taxa, including bivalves, jellyfish, Worms, sea cucumbers, centipedes, millipedes, scorpions, spiders, crustaceans, fish, amphibians are known. In addition, there are soft-bodied enigmas like the Tully monster, a bizarre worm-like creature that cannot be assigned to any known phylum. The absence of normal marine taxa and the sedimentology suggests that these fossils were quickly buried at the mouth of an estuary delta. When sediment-laden floods uh, of fresh water rapidly buried everything on the muddy bottom. The rotting tissues changed the chemistry of the mudstone so that iron carbonate could precipitate and nucleate around the fossil, forming the concretion. These concretions must have formed very early, for many of the fossils are undistorted, even though the surrounding shales have undergone much compaction. Other Lagerstätten. In addition to these classic localities, there is Lower Devonian Hansruck shale of western Germany, which produces over 400 species of animals with soft parts preserved, including segmented worms and trilobites, with all their soft limbs, gills, and antennae. The Middle Jurassic Posidonian Schiffer of Holzmaden, southern Germany, yields over 100 species of Jurassic marine life, including squids and ichthyosaurs, with their body outlines preserved as a dark film. One ichthyosaur was preserved in the process of giving birth. Both of these deposits are classic black shales formed in deep, stagnant water where there were few currents or scavengers to break up the carcasses. The Middle Eocene deposit at Messel in western Germany is an oil shale deposit formed at the bottom of a stagnant lake. Very different plants and animals, especially insects, fish, frogs, turtles, lizards, snakes, crocodiles, birds, and about 35 species of primitive mammals are preserved with impressions of the soft tissue and body outlines. There are also extraordinary examples of preservation of cell walls of plants, hair of mammals, scales from the wings of moths, color pattern on many of the insects, and the stomach contents of many of the animals. From all these examples, several general trends emerge. The best fossilization occurs when there is rapid burial and anoxic conditions to prevent scavenging, no reworking currents, and little or no diagenetic alteration to destroy the fossils. How good is the fossil record? To those who believe that the geological record is in any degree perfect will undoubtedly at once reject the theory of evolution. For my part, following out Lyell's metaphor, I look at the geological record as a history of the world imperfectly kept and written in a changing dialect of this history. We possess the last volume alone, deleting only two or three countries. Of this volume, only here and there are a short chapter has been preserved, and of each page, only here and there a few lines. All of the descriptive and anecdotal evidence we have just reviewed underlines the incompleteness of the fossil record. Can we also get a quantitative estimate of its quality? Can we answer in numerical terms the question how good is the fossil record? Let us start with some simple estimates. We have already estimated that there are 1.5 million described species or as many as 4.5 million described and undescribed species of organisms alive on Earth today. How many species are known as fossils? It turns out that there are only about 250,000 described species of fossil plants and animals presently known, or only 5% of the total for species living today. But the present is only one moment in geologic time. If we multiply the present diversity by the 600 million years that multicellular life has existed on this planet, the estimate is much worse. No matter how one does this calculation, it is clear that the quarter of a million species known as fossils represents only a tiny fraction of a percent of all species that have ever lived. But all is not lost. Almost half of the 1.5 million described species are insects which have a poor fossil record. Let us just focus on 9 well skeletonized phyla of marine invertebrates and see if we come up with better estimates. These 9 phyla are Protista, Archaeocyathra, Porifera, Nidaria, Bryozoa, Brachiopoda, Mollusca, Echinodermata, and Arthropoda, excluding insects. In these groups, there are about 150,000 living species, but over 180,000 fossil species. To translate these numbers into completeness estimates, we need to know the turnover rate of the species and the number of existing species through time. Different values have been used for each of these variables, but the results of the calculations are remarkably similar. Durham estimated that about 2.3 percentage of all the species in these nine phyla were fossilized. Valentine gave estimates that range from 4.5% to 13.6%. No matter which method we use, we must conclude that 85% to 97% of all the species in these nine well skeletonized phyla that have ever lived have never been fossilized. This is a very sobering estimate. It forces us to step back and reassess the limitations of almost any study based on fossil data. However, there is another consideration to keep in mind. The quality of the record depends on the level of detail we require. For a census of all the phyla or classes of invertebrates in a given sample, it would not be hard to get a complete sample. Obtaining every species is much harder. The reason for this is simple. A higher taxon, like a phylum or class, contains many different genera and species. If we obtain one species in each given phylum or class in a sample, we have a complete sample of phyla or classes with only a few specimens. But we need huge samples to get every species or even every family or genus that might have lived in a given time and place. In short, if we want to conduct large scale studies of evolutionary trends, we must concentrate on the higher taxonomic levels, kingdom, phyla, classes, and orders. We cannot expect to work on the species level, but in local problems, we can often select faunas with the best possible preservation, which might allow us to trust the species level data. Conclusions. The answer to the question, how good is the fossil record, is a complex one. For certain types of studies, it is excellent. For others, it is terrible. A good paleontologist knows when the data are worth pursuing and when they are so bad that any analysis is garbage in, garbage out. In the following chapters, we will review some of the excellent research that has taken advantage of the strengths of the fossil record. Naturally, we do not feature the many studies, mostly never published, that did not take these limitations into account. Okay. See you in the next class.